Ever wondered why airplanes experience drag, why wings stall, or why golf balls have dimples? Surprisingly, all of these are influenced by something only a few millimeters thick called the boundary layer. To get a better perspective, imagine an aircraft flying through the air. At first glance, it might seem like all of the air moves around the wing at roughly the same speed. But when we zoom in much closer, something interesting happens. Right next to the surface of the wing is an extremely thin layer of air where the velocity changes dramatically. This thin region is called the boundary layer. More specifically, the boundary layer is the region of fluid near a surface where the velocity changes from zero at the wall to the free stream velocity away from the surface. Even though this layer is very thin, it has a significant influence on drag, lift, flow separation, stall, and even heat transfer. So why does this boundary layer exist? The answer begins with one of the most important principles in fluid mechanics, the no-slip condition. Air is a viscous fluid. Because of viscosity, the air molecules that come into direct contact with the surface of the wing actually stick to it. This means the velocity of the air at the wall is exactly zero. However, the air farther away from the surface isn't touching the wing. It continues moving at the free stream velocity. Between these two regions, the air velocity gradually increases from zero to the free stream velocity. This gradual change in velocity creates the boundary layer. The boundary layer doesn't maintain the same thickness across the wing. At the leading edge, the boundary layer is extremely thin. As the airflow continues downstream, viscosity continues slowing nearby layers of air. Because this slowing effect spreads farther away from the surface, the boundary layer gradually becomes thicker. This means that the farther downstream you move, the thicker the boundary layer becomes. Not all boundary layers behave the same way, and there are two types of boundary layer with distinct characteristics and features: laminar boundary layers and turbulent boundary layers. In a laminar boundary layer, the air moves in smooth, orderly layers that remain nearly parallel to one another. Because there is very little mixing, laminar flow produces relatively low skin friction drag. This makes it highly desirable for improving aerodynamic efficiency. However, laminar flow has one important weakness. It contains relatively little energy near the surface, making it easier for the airflow to separate. A turbulent boundary layer behaves quite differently. Instead of smooth layers, the air moves in a chaotic, constantly mixing motion. Turbulence increases the thickness of the boundary layer and also increases skin friction drag. At first, that sounds like a disadvantage, but turbulent flow carries much more momentum close to the surface. That extra energy allows the airflow to remain attached to the wing much longer. So what determines whether a boundary layer is laminar or turbulent? One of the most important parameters is the Reynolds number. The Reynolds number compares inertial forces to viscous forces within a fluid. At relatively low Reynolds numbers, viscous forces dominate and the flow tends to remain laminar. As the Reynolds number increases, inertial forces become more important. Eventually, disturbances grow unstable and the boundary layer transitions into turbulence. Factors such as velocity, characteristic length, fluid density, and viscosity all influence the Reynolds number. As air flows around an airfoil, it experiences changing pressure. Sometimes the pressure decreases in the direction of flow. Other times, it increases. When pressure increases in the direction of the airflow, we call this an adverse pressure gradient. An adverse pressure gradient forces the airflow to slow down. If the air inside the boundary layer loses too much momentum, it may no longer have enough energy to continue following the surface. When the airflow can no longer follow the contour of the wing, it separates from the surface. This phenomenon is called flow separation. Flow separation creates a low-pressure wake behind the object. This dramatically increases pressure drag and can significantly reduce lift. If flow separation becomes severe on an aircraft wing, the wing can eventually stall. One of the major reasons engineers sometimes prefer a turbulent boundary layer is because it has enough energy to resist flow separation much longer than a laminar boundary layer. So far, we've discussed how boundary layers behave around airfoils, but these same principles appear throughout engineering, and one of the best examples is the golf ball. At first glance, you might think a perfectly smooth golf ball would travel farther through the air. Surprisingly, the opposite is true. The dimples on a golf ball intentionally trip the boundary layer from laminar to turbulent. Although a turbulent boundary layer creates slightly more skin friction drag, it carries more energy close to the surface. This extra energy allows the airflow to remain attached to the golf ball for a longer distance before separating. As a result, the wake behind the golf ball becomes much smaller, reducing pressure drag significantly. The reduction in pressure drag is much greater than the increase in skin friction drag, allowing the golf ball to travel much farther than a smooth ball would. So while dimples may seem like an odd design choice, they're actually a carefully engineered solution that uses boundary layer physics to improve aerodynamic performance. Although the boundary layer is only a thin region of fluid near a surface, it has an enormous impact on engineering. It influences drag, lift, heat transfer, flow separation, and ultimately the performance of everything from airplanes to golf balls. Understanding the boundary layer is one of the first major steps toward understanding fluid mechanics and aerodynamics as a whole. Thanks for watching, and I'll see you in the next one.